That is correct. Super easy reflections. Again, these congruent transformations, super easy. So let's just begin by reflecting a single point and just kind of talk about how it's going to work and that. So we're going to start with a point. We'll call it point P, since I have no imagination. And I'm going to reflect this point, okay? Now, I can't just reflect the point. I have to have a line of reflection. I have to have something to reflect it across, right? Okay, so we have to have some line of reflection. It doesn't really matter where that line of reflection is. I'll make it right here. You might be wondering why I'm really concentrating on getting that line good. You'll see in a minute. Okay, so here's our line of reflection. I suppose it could be a segment or a ray or something, but we always think of it as a line, okay? So what I want to do is I want to reflect this point across the line. Now let's think about where that point's going to end up if I reflect it across the line. Do you think it could end up down here? Do you think it could end up right here? How about up here like this? How about over here like this? Can you kind of see where it's going to be? It's not going to just flip over the line somehow. It's going to make a right angle here, and the distance away from the line that the point's going to end up is going to be exactly the same as this distance right here. So I'm going to call that point A. So I'm going to say that AP and AP prime are going to be congruent. And I'm just going to show you why I really worked on that line there for a second. So now I can take my paper and let me darken in point P a little bit. I'm just going to fold it across that line of reflection, and I'm going to come over here and like that. Can you see it? Hey, it worked. Even my little dots worked. So there is point P prime. So that's reflecting across a line of reflection. Now, if we happen to have a figure rather than just a point, let's say we had a segment. Let's say we have a segment right here. We'll call it PR. How will we reflect this segment? One point and then another point. Exactly. We're going to reflect. We don't reflect the segment. We reflect the individual points on the end of the segment. So if we just take this, flip it over here again, and color it in so I can see where point R prime is, then I can connect them. Starting to look like something now, isn't it? Okay, and let's say we have a triangle. PR, we'll call this one Q. So we have this triangle. So how do I reflect a polygon across? Yeah, each individual point. I just reflect each individual point. So I come over here like this and kind of rub that in a little bit. Can we see it? So there's Q prime. And then if I connect them, there you have it. It's kind of backward, isn't it? Right? But you can see exactly what's going on. If I connect one of these points with R prime, I want you to notice that they intersect the line of reflection at a right angle. They're perpendicular right there, aren't they? And if we talk about this point right here, we'll call it point B. What do we know about segment BR and segment BR prime? They're congruent. Okay, that's always going to be the case. And I also want you to notice that all of these connections between P prime, R prime, Q, Q prime. These three lines are parallel, aren't they? Okay? And if you look at that really closely, it might look like a three-dimensional figure. Yeah, it kind of does, doesn't it? Okay. So, all right, so that's how we do the basics of reflecting something across the line. However, we're going to do some of this on the coordinate plane, which makes our life a little bit easier. Because, you know, coloring that in really dark and then folding it right there and rubbing the paper, probably not something we want to do all the time, is it? Okay? But we can come over on a coordinate plane and we can talk about reflecting a point or something without having to do that. So let's just start with a point right here, point A. Now, if I'm going to reflect this, what would be a nice convenient line of reflection? The x-axis, right? Or the y-axis. Okay, so can we reflect this across the x-axis? Sure. Right now, it's directly above the 4 on the x-axis, and it's up here at 5, down here at -5. There's A prime. There's our point reflected. Can we reflect across the y-axis? Sure. We would just go to here at -4. So in that case, if we reflected that direction, A prime would end up right there. Okay? So you can reflect across the x-axis or the y-axis. And I want you to notice something. For 5, when we reflect across the x-axis, notice that the x-coordinate remains the same, but what happens to the y-coordinate? Okay. Do we have to graph something to know where it's reflected to then across the x-axis? No. If we just have some random point, 8327, and we want to reflect that across the x-axis, all we have to do is change the y-coordinate. There, it's reflected across the x-axis, isn't it? Easton just went, oh my gosh, that's the easiest thing I've ever seen in my life. The laziest thing? Well, I have told you that I am lazy, so whatever. Okay, so what if we're going to go across the y-axis instead of 4, 5? Where do we end up? -4, 5. So when we go across the y-axis, all we have to do is change the coordinates sign of the x-coordinate, and boom, we're across that axis. So I suppose we could make this a general rule that you might want to put in your notes or something like that. Let's see, I wonder if I can write it something like a mapping function, like xy is mapped onto something. So if I go across the x-axis, what is xy mapped onto? X opposite of y. That's correct. So there's the general rule. Do it all the time. Nose goes. Okay. And a reflection across the y-axis. Yep. xy is mapped onto the opposite of x and y. Now, I don't want you to think that if we reflect something across the x-axis that its y-coordinate's always going to be negative. Is that true? So if we started with 4, -3, and we reflected that across the x-axis, where would we be at? We'd be at 4, +3, wouldn't we? So this says the opposite of y, the opposite of whatever y is. It doesn't say it's a negative number. Same thing here. You know, if we had a point like -7, -9, and we reflected across the y-axis, it would be the opposite of whatever x is. So it would be +7, -9. So there you go. There's a general thing for reflecting stuff across an axis. Now, are there any, I better get another piece of graph paper. Are there any other lines on our coordinate plane? Oh wait, let's talk about something for a minute first. Hey, see that point right there? Can we reflect that across the x-axis? Sure we can. Okay, ready? Here's x. We'll call this point x. I'm going to reflect it across the x-axis. Boom! Done. Did you see that point flip over? It did. Trust me. You trust me, Logue? Okay. Can we reflect a point across the y-axis even if it's on the y-axis? Sure. If this is point R, where's R prime going to end up? Same exact point. The point is actually raised up, flipped over, and went back down on the y. Can you envision that?
Yeah.
Some of you are giving me a little look like maybe you don't trust me on that one, but that's how I think of it. Okay, even though it doesn't really move, I still think of the point as flipping, which is weird because points don't have any width or height or anything like that, do they? So it's like, how does it flip over? But something's got to be going on. So, all right. What other types of lines? What is, other than, well, I suppose we could have a line like this. What is the equation of this line? Okay, x equals -6. Could we reflect points across a vertical line? Okay, or maybe a horizontal line? What's the equation of this line right here? Okay, y equals -3. Have you noticed that I've been putting some questions like this on Alex lately? Yeah, so I want you to remember, if it goes through the x-axis, its equation is x equals something. If it goes through the y-axis, its equation is y equals something. You guys always want to do it backward. You always want to say, if it's going the same direction as the x-axis, you always want to say x equals something, but it's opposite from that, isn't it? So I need you to think, if it goes through the y-axis, then it's y equals something. If it goes through the x-axis, then it's x equals something, okay? So it wouldn't be a big deal to reflect a point across one of those, would it? I mean, if I just drew some random point here, could we reflect it across the line x equals -6? Sure. You notice it's 1, 2, 3, 4 on a perpendicular line, so 1, 2, 3, 4, there we go. Okay, so we can reflect things across vertical and horizontal lines fairly easily. Other lines that we might run into. Yep, y equals x. Y equals x. Y equals 1x plus 0, right? 1x plus 0? Okay. So, reflecting a point across this line, it's helpful, especially at first if you actually have the graph and everything. But let's just put a point on here. We'll call it point A. And we need to reflect it across this line. Does it need to go at a right angle? It needs to go at a right angle, and it needs to end up exactly the same distance away, doesn't it? Okay? So here's what I do sometimes. I kind of look at the diagonals. How many diagonals is it over to the line? Well, it's 1, 2, 3 diagonals, isn't it? So going the other way, we just go 1, 2, 3 diagonals. I think A prime might be right there. What do you think? Now we were at 2, 8. Where are we now? 8, 2. Anybody come up with a conjecture about a general rule for reflecting across the x-axis? Or sorry, the line y equals x? You think that's a possibility? Should we test it again just to? Yeah. Let's do it. Let's do another one. I'll do this one in red. So I'll put a point right there. So if I do diagonal wise, 1, 2, 3, ooh, and a half? 3.5 diagonals? All right, so a half and then 1, 2, 3. So here's point P, here's point P prime. Does it look right?
Yeah.
Okay, you can also do it this way. You can go, okay, to get to the X line, I can go down 1, 2, 3, 4, 5, 6, 7. Okay, so then I go over 1, 2, 3, 4, 5, 6, 7. You don't have to count diagonals, you can count like that. Or if I were to count this direction, it would be 7 units over, so then what would I do? 7 units down. Okay, so I was at the point -7, 0, and that was the pre-image. Where's the image? Okay, so it worked twice. Do you think that general rule-ish kind of thing? Okay, so I think that's something we might want to put in our notes. So across the line y equals x, xy is mapped onto, yeah, yx. We don't change signs or anything, do we? I wonder if there's another line we might think about reflecting across. Y equals the opposite of x. Okay, plus 0. -1/1. You guys good with this? Yeah. So the y-intercept's 0 and the slope is down 1/1. So this is the line that goes through the origin at a 45 downward. Let's do one over in this quadrant. What quadrant is this? Fourth, okay. So if I just put a point here somewhere, we'll call it point R. Can we reflect it? Let's see. I'm going to count diagonals. 1, 2, and a half. A half, 1, 2. R prime. Let's see, does that look like they're connected by a perpendicular line? Does from RP and R prime P, do they look congruent? There you go. So R is the point, where are we? 4, -9? R prime, am I keeping this on the, okay. R prime is at 9, -4. Woo! So let me write that. R was at 4, -9, and it was mapped to R prime at 9, -4. What happened?
The x and y values swapped and became opposites.
So the x and the y value changed places, and they changed signs, didn't they? So let's go back to our notes. So a reflection across this line let's see. So we take the opposite of whatever x is and we put it opposite of whatever x is and we put it over here. And we take the opposite of whatever y is and we put it here. So for the positive slope, we just flip them. And for the negative slope, we flip it and change the sign. Okay. If we did more than 1 point, so we've got, let's say we got a point here. So we have a segment rather than just a point that we're reflecting. So I'll do the next one and should do this one in red over here. So 1, 2, 3 diagonals, 1, 2, 3 diagonals. This is point P. Here's P prime. What do you guys notice about RP and R prime, P prime? The segments. What do you notice about the segments? They're congruent. That's kind of a big deal. That's the reflection postulate. It says a reflection is a rigid motion or a congruent transfer. I like to call it congruent transformation, but we got to know rigid motion as well. If we had a whole triangle over here, so this is Q, and we reflect that one as well. So 1.5 diagonals, a half, 1 diagonal. So here's Q prime. Notice our two triangles? Congruent? It's a congruent transformation, just like a translation is. So it's a rigid motion or a congruent transformation. Okay, turn to page 184. At the bottom of that page, example 4, we're going to talk about there a particular type of transformation called a glide reflection. A glide reflection is a composition, but it's not a composition where you do two translations or two reflections. It's a particular one where you do a glide, you do a slide or a translation, and then you do a reflection in that order. It has to be done in that order. So a glide reflection always is a translation reflection. If you look at the example, everyone see the blue triangle? Okay, so they do a translation over to the red. They just slide it to the left, don't they? And then we do a reflection across the, isn't it across the x-axis? Across the x-axis. There. That is a glide reflection. And you just have to be aware that whenever we talk about a glide reflection, that particular type of composition, it has to be in that order. So we don't call it a glide reflection because we reflect and then we glide. We call it a glide reflection because and we slide and then we reflect. That's right. Okay. Identifying lines of symmetry. Does your face have a line of symmetry? You better hope so. Yeah, you better hope so. When our faces don't have a line of symmetry, people often look at us strangely because most people's faces have that line of symmetry on them, don't they? Okay, your eyes here. In fact, a lot of like celebrities and people like that, if you look at this line of reflection. Now, is there more than one line of reflection on a face? Is there a place where you could fold your face in half and make it map onto itself? Other than just that one vertical line? I think you're overthinking it. You may be overthinking it. You think there's more than one? No. Nah. Okay, so we got our ears here. Like a lot of celebrities or people that we find very attractive for some reason, their face is very, very symmetrical, and the distance their eyes are from that line is exactly the same. And I don't know. I'm not that attractive, so it's hard for me to envision this. So, but there you go. Have you ever seen the pictures where it shows half of somebody's face, and then instead of showing the whole face, they actually take this side and they reflect it, and so it looks over here, it's the exact reflection, and then they take this side of the face and reflect it, and they come up with two different pictures, and the expression on the face looks quite different. Maybe we can look at those tomorrow. But do you notice on my guy, see how he's smiling a little more with this side of his face? So if we were to reflect that over, he ends up smiling a bigger smile. And on this side of his face, he's not smiling quite as much. And we all have a tendency to do that. In fact, so much so that dogs will always look at one side of your face more than the other. when they track where the dog is looking, when it's trying to tell if you're happy or sad or mad at the dog, they have a tendency to look at one side of our face more than the other side because they can read the emotion better on that side of your face. So you're all kind of two-faced, I guess, is the moral of that story. Anyway, we'll look at some of those pictures that are kind of cool. Check out the butterfly. Does it have a line of reflection?
Yes.
What would happen if the butterfly did not have a line of reflection? That's right. So when you were a little kid and you caught a butterfly, and it looked so pretty and perfect and everything, and then, I don't know if I can draw it pretty and perfect. Pretend that's pretty and perfect and everything. And then maybe you tore a little bit of its wing off when you were holding on to it, so that part was gone. And then the butterfly tried to fly. Didn't happen, did it? No, it didn't happen. What about an airplane? Does it need to have a line of symmetry? What about a car? Yeah. When the wind's hitting a car, is it going to go down the road straight if it's not symmetrical? It's not, is it? Okay. What about a race car that only races on an oval track, one of these oval track cars, NASCAR? Are they symmetrical? No, they're not symmetrical. How come? Yeah, they only turn left. They only turn left. And so, yeah, so they build the car so it turns left. Now, if you put that car and you tried to go the other direction around that track, bad things would happen. Bad things would happen. Okay? Their gas tanks, the gas tanks on a NASCAR are even on this side of the car, on the inside of the car, and they keep all of the weight that they possibly can down there. And the front of the car isn't exactly flat, and so they only have to turn left. So if you only have to turn left, you don't have to be symmetrical. Otherwise, probably a good idea to be symmetrical. Okay. So you see there next to the butterfly, some of the polygons have one line of reflection. Some of them have multiple lines of reflection. And the thing I want you to notice is the more regular the figure, the more lines of reflection it's going to have. Even if it doesn't have very many sides, so if a polygon has the fewest sides possible, okay, so if it's an isosceles triangle, how many lines of reflection will it have? Just one. Okay, we just have one line of reflection. But if it's an equilateral triangle, if it's more regular, that's right, it's going to have 3 lines of reflection. So the more regular a polygon is, the more lines of reflection it'll have. Okay, so now let's talk about something kind of cool. So a little bit of a construction problem here for us. So we've got a house right here, and we need to get power to that house right there. And then we have this other house right here, and we need to get power to it. And we have this line, this power line coming along. And at some point we need to put a new pole in, and we need to run a power line over to this house and over to this house. Now we can put that power pole, we can put it anywhere along the line that we like. And then we can, from that pole, we could run a line over to here and then a line over to here. But we want a minimum distance. We don't want it to be any longer than we have to, because that cable is very expensive. You guys ever seen the cable they run to a house? Yeah, it's big around. It costs a few dollars a foot. It's not cheap. And if every time you can save some money, it's going to help. Okay, so where do we want to locate this pole? It might seem that it doesn't really matter. It might seem like, you know what, if we went to here and then we went up here like this, or so we have a short side and a long side, or let's say we went way over here first and then went up, it might seem like, well, is there a difference? What if we went more to right in the center between them? Does it do you think it would make any difference, or do you think the two of them would add up to the same amount regardless?
The one closer to the deal would probably be shorter.
You got a conjecture? Who thinks it doesn't matter where we put the point as long as it's between the, like you wouldn't want to put it over here, would you? No, we're way over here, right? Okay. Does it seem, who thinks it doesn't really matter? Yeah. Seems like it doesn't really matter. In fact, it matters. It does matter. That was a good guess, though, because it kind of seems like, who cares? But, you know what? It does matter. So, what we want to do to find the minimum distance, to locate where we want to put that pole, is we want to reflect one of these points across the line, and then we want to connect it to the other point, and that's going to give us our line. Now, it doesn't matter which one you do, okay? We can reflect either point across. Now, I'm not going to do the thing where I drew really dark and then I folded it over. I'm going to show you a little construction thing. So remember finding a line that is perpendicular to this line and goes through this point? Remember doing construction? So we put our compass here like this, and we just make an arc like that so that these 2 points are the same distance from point P. And then we come over here, and we can adjust this now if we like, but we make an arc, and then we don't adjust our compass, and we come over here like this, same arc. So now when I connect that to the intersection, okay, what kind of angle I got right here? Okay, I've got a right angle. So that's half the battle, isn't it?
Yep.
So this point, to reflect it across, it's got to be on a perpendicular line, doesn't it? And it doesn't have to be the same distance away. Well, we can do the distance thing easy. See, we can put our compass like that, and we can, that distance right there, come down here. Right there is P prime. Now, if I go from P prime up here to this other house, that point right there, that's where I want to put the pole. And that distance right there, even though it seems a little strange, if you put the pole right there, that will be the minimum distance. That'll be the shortest distance, like that. There's lots of applications for this. We'll talk about a few of them, but there you go. So let's get started on this assignment. It's chapter 4.2. I'll have you do that tomorrow, and we'll do a few together as well.